without further ado, I'm going to pass this off to Kurt Hull, who's the Vice Chair of Sustainable Building Manitoba, as well as the Director over at Climate Change Connection, as well as so many other things. For those who know Kurt, he's very active in the community. And so he's going to introduce our panelists and help us guide us through this discussion. So thank you, Kurt, and everyone who's here.
Thank you very much, Laura. And can everyone see my screen there? My presentation. So what we're going to do in the next hour and a half, and by the way, we're hoping that this is going to be an hour and a half, of which we're going to be investigating the question, how can we heat all of our buildings, old and new, affordably without natural gas? And the format of this session is that we're going to, there's going to be four of us. There's going to be Ed Lorenz, Michael Stocki, and Donald Proven, and myself, and each of us are going to have 15 minutes to do a presentation. My presentation is going to be a framing presentation, give us sort of a framework for the question and a bit of the answer, and then each of the other three have got specialties of special view of the solution to the problem, and so that's the way we're going to do this, and hopefully there we go. So to the question of how do we heat our buildings affordably without fossil fuels is the question before us. And that's what we're going to be investigating. So why do we need to do this? It's not just an idea that at random. Instead, it's a response to an imperative, which was really made clear to us in 2008 around Thanksgiving. The IPCC, the Intergovernmental Panel on Climate Change, came out with this really milestone work, the 1.5 report. And in that report, it talks about the curve that we're on for global warming, for global heating. That the red line that you see there is the trajectory that we're on, and if we just continue to keep doing what we're doing, that straight line will continue to be a straight line into really oblivion, into a climate that will not be able to support our civilization. Instead, we want to bend that curve into the gray area, around 1.5, ideally 1.5 to 2 degrees of warming. That would be consistent with the climate that's supported our civilization up till now. So in order to do that, we have to reduce our emissions really dramatically. And that's the imperative that's before us. We need to be able to respond to this in a very short time frame. We're already in 2020. We got to get to 0 or thereabouts by 2050 or thereabouts. Because even in Manitoba, like if you talk about climate change in Manitoba, most of the time they go, oh, we're going to have warmer winters. Well, maybe, but there's also consequences that are really much more dire for other people. And we're talking about climate migrants. And when climate migrations happen on a large scale, potentially you wind up with global conflicts. And when you have global conflicts, besides the human tragedy that results and the devastation, there's also economic consequences. And when those things may be happening halfway around the world, and we don't necessarily see them other than on the news, the consequences economically can be immediate and felt here very, very immediately and sharply. So therefore, we have a challenge that we need to meet. And if we're going to address that here, really what we're talking about is building our resilience. In other words, we have to be able to meet our essential needs ourselves without fossil fuel. And when I talk about essential needs, what we're talking about are the 3 areas of food, transportation, and shelter. And so there are questions within those 3 areas that we need to be able to, challenges that we need to be able to address. We need to be able to feed ourselves locally without fossil fuel fertilizers. We need to be able to move all goods and people without gasoline or diesel. And then the challenge that we're dealing with here today, which is we have to be able to heat all of our buildings, old and new, affordably and without natural gas. So that's what we need to do. That's the challenge before us and what we're addressing here today. And hopefully this will be a conversation that will carry on. This is an objective or a theme that Sustainable Building Manitoba will be carrying forward at least through the next year. And so in order to meet this challenge, I'm going to give the sort of the real key themes of solution in order to bring our greenhouse gas emissions down. Well, we can't just change from natural gas to electricity. But yet we've been increasing our dependence on natural gas over the last few decades continuously. We're on average in the last 6 years or so, we've been adding about 2,400 new natural gas customers every year. And we've been adding pipeline into the distribution system. So we're headed in the wrong direction. But we can't just do a switch from natural gas to electricity. Hydro, we don't, as much as we value our hydro resource and it's wonderful, we want to make sure that we make use of it as efficiently as possible. Because even though from an energy perspective, if we were to heat all of our buildings electrically, we would only have to add about 10% to hydro's annual energy generation number. But that's not the important number. Energy is not the important number, it's power, distribution, the ability to heat our homes on that cold January night when everybody's got their heater on. And if that is all electric, then that occurred in January of 2019 when we had a demand of just under 5,000 megawatts. And hydro's capacity is around 5,200 megawatts. And when Kiosk comes online, we're talking about just under 6,000 megawatts. And the studies that I've seen that hydro is using for their projections, if we were to heat electrically just with like resistive electricity, they're saying we would need another 7,000 megawatts. So we can't just switch fuels from gas to electric, and hydro can't meet the demand. So the cost of natural gas is not working in our favor. The cost of natural gas is going down as the cost of electricity is going up. So that's working against us. But hydro could make more money if they were to sell electricity at the domestic rate rather than exporting it at the 2 cents a kilowatt hour that they have been in the past. So there's opportunity for hydro if they were to sell more domestically. And our economy is currently leaking money by importing these fossil fuels. So there are opportunities when it comes to addressing this issue, this challenge. So the pathway in general terms is, first of all, the envelope of our buildings, making our buildings more efficient. And we need to make our new buildings more efficient through an enhancement of the building codes. It's now not really as challenging as it needs to be, put it that way. We need to make use of techniques like passive house in building construction. This is the first certified passive house in Manitoba that was just certified a couple of years ago. And perhaps we need to build them with from kits like this. Retrofit also is a huge challenge, huge challenge. That might be done, where hopefully we'll have an event in the near future on this prefabricated exterior energy retrofit initiative. And this is a familiar face here. This is Donald and one of his sites using a Larson truss for a retrofit, exterior retrofit. And there's opportunities for good jobs. Heating, making more use of solar passively, making more use of biomass, making more use of district heating, and the three key aspects of heat pump. We've got ground source heat pump, lake or water or stream-based heat pump, and air source heat pump. And I called up the wrong presentation. The last slide that I was going to show has to do with energy storage. And energy storage is where we can take these renewable sources, which are intermittent, and store the energy. And there's various strategies for that, including batteries or chemical storage. potentially, or the use of hydrogen, electrolysis, hydrogen that comes from electrolysis. So that, in a nutshell, is the frame that we're going to be diving into more deeply now with our next presenter. And so our next presenter is going to be Donald Proven. And Donald is a certified passive house consultant and tradesperson. And 8 years ago, he and his uncle Randy and his cousin Evan and his father Rick Proven started Sun Certified Builders Co-op. Sun Certified Co-op delivers outstanding high-performance building design, construction, and renovation solutions. They've been improving building energy performance in existing homes and building new ones using Passive House Institute energy modeling tools and building science principles. He has over 30 years of high-performance building experience. Donald, please give us your perspectives on this challenge.
Good afternoon, everyone. Can you hear me with the audio? I'm in a slightly remote. Okay, I'm going to share my screen. My presentation is going to be fairly quick, I'm hoping. Can everybody see? That's not the slide view. That's from current slide. How's that? So, Kurt invited me to the Sustainable Buildings Manitoba event, and the question was, how do we heat our homes without fossil fuels? I guess our take from Sun Certified's perspective is to do what we've been doing all along, which is build high-performance buildings. This is just a quick sample of some of our projects. Some of the folks who are on the call here live in a few of these houses. One of the key aspects to how do we achieve this goal, heat our homes without fossil fuels, is education. Pre-COVID, we were able to travel to Alaska to do a presentation on this very thing. There was quite a turnout, as you see, in Anchorage, and it was kind of an interesting experience for us. We hadn't done really anything down or in the States. So I want to jump right in to solutions. Kurt touched briefly on some of the basics, and I'm going to do that as well. So it comes right down to how do we reduce, in our mind, the building energy demand to the point where we can switch to electricity. And so he indicated, correctly in our view, that you have to address the building envelope. So new buildings have to be high performance, and we have to retrofit a fair number of the existing buildings to do the same. Now there are lots of numbers out there talking about the percentage that is required to achieve the 2050 for retrofitting, and it's a pretty steep hill to climb. So there's going to be some challenges on the retrofit side. We feel we have the new buildings I think are solved in terms of my view. So we use the Passive House standards, as Kurt indicated, to design and model and build our projects. I'll talk a bit about Passive House very briefly. It's just a design and modeling tool. It's kind of what we think are the best available because it's verified. It uses third-party verifications for the targets that you're setting. And it sets out a very clear array of building performance targets, and we start adding our own. So as Kurt indicated, you need drastic load reductions to allow the switch to electricity and the potential for renewables. There's really no other way to go about this except that load reduction. So we do it through the envelope, and we'll get to that. In our view anyway, the technical challenges are no longer an obstacle. You know, we're trying to build our walls, prefabricate them off-site, have them shipped to the site. There's what it looks like. We don't have a grand factory yet, but we're going to. It looks simple. It looks a little bit different from a regular wall. I can talk about some of the features that make it different. There's lots of space for cellulose, which is the insulation. We've paid attention to air movement and water vapor movement, and drainage and air tightness are all part of the system. We're continually trying to improve what we do, because the building trade or the building industry has undergone a significant change in I would say the last 15 years or so, but most of that is related to technology. The design and modeling and technique aspect of how we go about building, especially single-family dwellings, has really lagged behind, we feel. There's been changes in the way we go about building larger buildings, which we don't involve ourselves in so much yet, but there's been lots of progress, but the single-family dwelling industry has really lagged behind. We always say that we're still stuck in the 1950s in terms of how we build our single-family dwellings. Kurt mentioned heat pumps, and heat pumps, whether it's ground source, air source, or different kinds, it's mainly those two, they're going to be really the only option we have to reduce the resistance heating load, and to do that efficiently, and the key here is affordably in a increasingly warming climate. If we don't take into account the climate change that's already happening when we're modeling and designing our buildings, we're just going to have to revisit those buildings in the future, and we don't want to do that. We want to take that into account now. For Sun certified builders, the building performance challenges, we feel that we can meet most of them in a reasonable fashion here in Manitoba, and so we've kind of started to look at other and we feel equally important aspects, and embodied carbon, as Kurt pointed out, is one of them. That's the carbon that gets tied into your building with the materials and the methods and the transportation when you go to build a building. So it's all that emission that occurs before you even start building. And the reason this is important is because if we build buildings that have very low embodied carbon, and if we build them using methods and techniques that reduce the energy load to the point where we can put renewables on, which is what you're seeing there, solar PV on the roof, then the buildings can start having a net positive impact on the global CO or carbon balance. And that means that our buildings can contribute to the solution to our 2050 targets. And because the building trade or the industry is quite large, keep on trucking up. Every time I change my mouse position, I can't advance my screen. Because the building industry can have a fairly significant impact on the carbon balance by using our buildings and how we do this as one of the tools. That gives us, I wouldn't say a buffer, but that gives us a bit of leeway to address the other two key areas, food production and transportation in the society. If we don't do that, then we're missing these huge pieces of the puzzle. It can't be independent of those other solutions. We have to work with that. And if we have buildings that can store carbon for long periods of time, we feel we can contribute to the solution, and that gives us more time to deal with other aspects of the society. So in the design process, you have to set goals for your buildings. Otherwise, you're not really, you're not going to achieve any sort of target. We're not going to achieve savings economically with durability or energy efficiency unless you have something that you're going to shoot for. And so the energy, durability, comfort, carbon now, and economic performance have to be targets that we're shooting for. And Passive House, as I mentioned, is a tool that we use to provide us with targets and methods and modeling to achieve those high performance buildings. So these are the targets we're shooting for. I don't really want to have to go through the individual values because it's a little bit technical. And as I said, for the most part, these buildings can be built. There's a few of folks in the audience that are living in those buildings now that we've used these ideas and methods to retrofit or build their new houses. And so, you know, we haven't met the Passive House targets here in Manitoba. It's fairly expensive to do so, but we've used these as guidance to try and get as close as we can. It's talking about yearly heating demand and peak energy or heat loads, which are about 75 to 90% less than a typical building. The primary energy is the all-in energy for the houses. You have to have air tightness so that you're not wasting energy with leakage, and it makes for a comfortable building. And then there's windows or provide free solar energy from the sun. That's a fairly old passive solar idea that's been around since the since the 70s. Of course, the sun's been around for quite a bit longer. And then ventilation comes along with sealing up your building. But these are technical challenges that have been addressed, I feel, for the most part. There's plenty of places where City of Vancouver is one of them in Canada, where they're using these types of targets for their step code to move the whole city in the direction that we want to go. City of Vancouver is one of the most aggressive in terms of getting us down the path to high performance. These, again, are the principles that guide how we do the buildings. Thermal insulation, Kurt touched on that. The building enclosure, you have to start with the fabric of the building as part of your design. You have to have a system in place to achieve that overall building thermal performance. You can't have parts of the building poking to the exterior that are going to conduct cold and heat and moisture. That's called thermal bridge-free design. You have to have really good windows so that they don't leak and they don't make it uncomfortable to sit by at a cold -40 night. You have to have very good ventilation so that your building's not going to have problems interior with moisture and with stuffy air. You have to be airtight to begin with so that, as again, you're not leaking that heat and moisture into the system. And there's some simplicity of shape and some design that goes into designing these buildings. I want to talk about economic efficiency because that's a an item that comes up frequently. We get asked all the time, well, how much more expensive is it to build an efficient building? And we have tools available to tell us overall that it does cost more generally, because we're putting in quite a bit of insulation and some better windows and heat recovery ventilator and things like that. But overall, when you decide to go down the high performance path, you end up with economic return almost immediately. I'm just going to talk, I've borrowed this from CFAR Building Analytics. We've used them to economically model our buildings and how we do this. They've based most of their modeling and how they go about doing this on our buildings and our retrofits. So it's somewhat, it's not a conflict of interest though. So this is overall for Manitoba. They've taken an average of, there's 6,350 new homes per year were built in the last few years. So they've taken that, chopped it down to 5,000 to be conservative, and taken that by 10 years. So that's 50,000 houses. They've come up with a method to evaluate how much it costs to own and operate a house over a period of time. It doesn't have to be a house, it can be a building. So that's called the total cost of building ownership. You take that over a span of time. That accounts for not just your energy bills, it accounts for your mortgage, it accounts for your insurance, it accounts for your maintenance and operation costs, which are part of owning and operating a building. We all know that. So they take those numbers, they've compared it from a co-built to a high performance, and they've assigned with their tools some numbers. So for a code-built home over the 50,000 houses, these are single family dwellings we're talking about, there's a cost over 60 years to own and operate. That works out to $48 billion. There's a cost to own and operate the high performance buildings. It's less, it's $31 billion, still a significant amount of money. But the economic efficiency, the savings that are incurred to going to high performance is about $17 billion. So that's over a period of 60 years, but that's still $283 million per year. And that's just for the single family dwellings that are built. And so if that amount of capital is directed into, say, retrofit programs, education for building trades to bring the level of performance of our buildings up, to subsidize PV and geothermal and heat pumps when you're going about the transition from natural gas to electricity, there's capital available if we follow this path, because the high performance buildings allows for those savings. And we can, these numbers are based on accounting principles and basic math. So Kurt touched on this fairly steep hill. I think I'm going to end off here fairly quickly, that we have to climb to reach the 2050 targets. There's been work done lately talking about embodied carbon in the buildings. I touched on that briefly. We can't net zero energy our way out of that, because there's carbon going into the buildings that we have to account for. It's about 10% of a typical building. It's not a whole lot. Or sorry, the embodied carbon is 90% of the emissions if you have a high performance electric powered building. The operation of the building is only about 10%. So if you don't address the embodied carbon, we're not going to be able to achieve these targets. So embodied carbon is the next thing performance-wise that we have to consider. And that means building with plant-based materials, wood, and for our view, it's cellulose as the insulation. So how do you go about getting off natural gas? My uncle Randy used to tell me all the time, just do it. And about 30 years ago, that's what we started to do. That's the key here is that we can't get bogged down in the technicalities. This is achievable on a mass scale if we decide to do it. The society's done that before in mass deployment of our economy to meet various challenges. World War II, our economy ramped up drastically. We can do this. It's totally doable. It just takes us deciding that it has to be done now and moving ahead and improving as we go. So that's our view. It's achievable. So thanks for the opportunity, and I'll turn it over to Kurt.
Thanks very much, Donald. Thanks for giving us that overview of the importance of efficiency, efficient building design and retrofits.
Yeah,
our next presenter is Ed Lorenz, and Ed is the founder and principal of GeoOptimize. He has worked in various roles in the geothermal industry since 1982. Installation, my screen just changed, my script is gone. I'll put it back over here. Okay, Ed's been working in geothermal since 1982. Installation contractor, equipment distributor, and manufacturer. He has pioneered the use of heat pumps in many diverse applications. His portfolio includes local projects some of us may recognize: Seasons of Tuxedo Mall, Waterfront Neighborhood Center in Toronto. He did the Alt Hotel in downtown Winnipeg, Toronto Emergency Medical Service Building, and the Steinbeck Credit Union in Winnipeg. He also has projects outside of Canada, including the current one, the proposed Obama Library in Chicago, John Hopkins Correctional Center in Australia, and the IKEA store in Centennial, Colorado. So share your view on this with us, please, Ed.
Thanks, Kurt. Yeah, I'll give you a quick overview of what geothermal is, if you're not familiar with it. Basically, what we're doing is burying a bunch of pipe in the ground and transferring energy back and forth between the building and the ground. So basically,
Ed,
oh,
you
yes?
may want to just hit play on your slideshow. Otherwise, we're seeing your PowerPoint without it being a presentation.
Oh, I'm sorry. Okay, is it? Okay, is that better? Sorry.
Yep.
Okay. The ground itself in Manitoba is about 45 degrees Fahrenheit or about 7 degrees Celsius. And we can pull heat from that very easily. It's compared to an air source heat pump, the ground's temperature stays fairly constant. So it allows us to take heat from it all winter long without any auxiliary. It also allows us to dump heat into the ground very easily when we're cooling a building. So the way we do that basically is burying plastic pipe in the ground, very similar to the pipe that is used by the gas industry to deliver gas to a house, but we're using it to move energy from the ground to the building. Different ways of getting the pipe in the ground: vertical boreholes, laying it in large excavations, drilling horizontally, laying it in the bottom of a lake. People are starting to use it by integrating the pipe into foundation systems in buildings, tunnels for subways or whatever, sewer lines, a lot of different places that heat is available from. One of the problems with natural gas is that if we're installing new gas pipelines right now, those pipelines are typically amortized over about 80 to 85 years. That's what helps make the cost of gas so inexpensive. So basically what we're doing is looking at what's starting to happen in a number of cities in the US. Let this play for a second. what's happening in a number of cities in the US is gas lines expansion is being banned. This is an interesting occurrence in Massachusetts. Eversource is one of the large gas and electric utilities in Minnesota. They're basically starting to build geothermal utilities. Instead of installing more gas pipelines, they're installing ground loops. And to be able to make the conversion from natural gas to electricity, we don't really have to build more dams to be able to accomplish that. For example, the Kiosk Dam will produce about 695 megawatts of power, or about 4,400 gigawatt hours of energy annually. Cost of building it, roughly 10.5 billion, or about $15,000 per kilowatt by the time it's delivered to Winnipeg. If you're looking at a single family home, there's 130,000 of them in Manitoba that are heated electrically, electric furnaces or electric baseboards. If they were converted to a geothermal system, they would reduce electrical demand by about over 900 megawatts every winter. So to reduce the peak demand, it will reduce demand by more than Kiosk produces. The cost to convert all of the homes would be under $4 billion, about 60% less than building the Kiosk Dam, and it will produce about 30% more power at a cost of about $4,200 per kilowatt. That's doesn't have to be produced. We don't need the power lines to deliver it. It has implications throughout the whole system. So a typical single family home, it will use about, for electric heat, it'll use about 17,000 kilowatt hours for heating, about 700 or 800 for cooling the building. The ground source will reduce that electrical demand to just under 5,000 kilowatt hours. And more importantly, it'll reduces the electrical peak demand by about 7.1 kilowatts. So it reduces the kilowatt hour consumption by about over 14,000 kilowatt hours, reduces demand by about over 7 kilowatts. So if we compare building the Kiosk Dam, those are the bars in blue, it produces less peak power than converting all of the homes, electrically heated homes, this is just single family homes, to geothermal systems. It won't produce as much energy because the dam is running probably about 70 or 80% of the time. We're heating the buildings probably about 30% of the time. The cost per kilowatt, that's either you're reducing the demand, the cost of making the power available by about 60 or 70%. Problems, especially in areas that are serviced by natural gas, like in the bigger cities, there sometimes isn't enough room to easily install a ground heat exchanger. A couple of options, and this is what I've done in my own house, is integrate solar thermal with a ground source system. So basically I'm taking solar heat, dumping it into a ground loop so that I've got more heat available in the winter, because in our climate, we're drawing about 10 times more heat out of the ground than we're putting back into it. And this helps balance the loads, makes the system operate a bit more efficiently. On a larger scale, community scale, there are district energy sharing systems that can work and are being built in cities right now, including by gas companies in Massachusetts. Examples: in almost every Canadian community has an ice rink. Winnipeg has about 40 or 50 ice rinks, ice arenas, and curling clubs. They get rid of a lot of heat. They just dissipate into the atmosphere. So if we take a twin hockey rink, and this is based on the Dakota Community Center, we can't use all of the heat to heat the building, heat that's needed in that building, within that building. This is graphically illustrates how much cooling is done versus how much heating is needed in that building. So we're getting rid of an awful lot of heat. About 6 times more heat is being dumped into the ground than we're pulling from it. There's several nearby buildings, including the community center. There's a library, there's a school, there's a personal care home. 12,200 square meters of building area, even that can't absorb all of the heat that's available from the ice rink, that's wasted from the ice rink. Typical energy load profile in a Winnipeg house does an awful lot of heating in a year, does a bit of cooling in a few months in the summertime. If we connect a number of homes to that system as well, and in this case, we're looking at about 109 homes can be connected to it before we balance the amount of energy that we're getting rid of from the ice rinks that we can use to heat the houses and buildings right around that ice arena. University campuses are starting to do this. Ball State University, Missouri State University of Science and Technology, Colorado Mesa University have already converted their campuses like this. And this can be done cost effectively, one building at a time. As the budget becomes available, they can add more buildings, they can add more ground heat exchanger. Moving and then connecting the buildings to each other and to the ground heat exchangers allows us to move heat from this building that's being cooled to these buildings that are being heated. This can be expanded organically to other parts of the campus as we go through the whole project. So this is Bemidji State University in Minnesota. They're looking at 23 buildings, and all we're doing is moving energy around a conveyor belt from one building to another, and then storing excess energy in a ground heat exchanger when we can't use it, pulling energy from the ground heat exchanger when we need it in the winter. Buildings that have been done in Manitoba, Altotel, Steinbach Credit Union, Windsor Estates, apartments in Porters of Prairie, school in just outside of Morden, Arbor Gate School, Churchill High School in Winnipeg, nursing center at the College St. Boniface, or University St. Boniface. The small district system in Winnipeg at the polar bear exhibit. See the polar bears swimming around and the seals swimming around, taking heat from that in the summertime to keep the bears cool. It helps heat some of the buildings, provide heat, and vice versa. In industrial applications, dairies use an awful lot of energy to cool the milk. They have to cool it within half an hour after after it's being milked. That heat, instead of dumping the heat to the outside, that can be used to make hot water. That's used to clean the facility and to provide warmer water for the cows so that they drink more milk. Potato storage, they have to give off heat all winter long. That's the nature of the material. Same with nursery trees. They give off a lot of heat, and that can be used to heat the machine shop next door or the house on the farmyard. Producing apple cider, and the heat taken from that process, fermenting process, can be used to heat the building. On commercial buildings, one of the comments is that the electrifying the buildings will require more energy. And this is on a typical commercial building that's heated with natural gas. Here's how much electricity is used during the year. The peak electrical demand up to about, in this case, up to about 50 kilowatts in summer and about 20 kilowatts in the winter. And this is how much energy is used, how many kilowatt hours. If it's converted to a geothermal system, the amount of kilowatt hours actually goes up a little bit, which provides more revenue. More importantly, it reduces the peak electrical demand by about 40%. So instead of having a big peak load in the summertime and less load in the winter, it does increase the winter load a little bit. But when you combine this with converting electrically heated homes to geothermal systems, the overall impact is very little on the current electrical infrastructure. It produces more kilowatt hours, and as Kurt was saying earlier, that can be sold in Manitoba at a higher cost, giving more profit for revenue for the Manitoba Hydro, and at the same time, it doesn't have an impact on their peak electrical demand. You don't have to build more dams to be able to produce the power. It's already there. So buildings that have been done in Manitoba, and around the world. This is happening, and it's happening quite regularly. Thank you.
Wow. I'm always learning so much and getting inspired by every time I see your presentations, and they're always different, Ed. But this is really mind-blowing stuff here. We'll come back to this. I've got lots of questions, but before we do, we're going to hear from Michael Stocki. Hopefully, I'm pronouncing your name, Mike. Mostly, Michael. Is it Stocki? Stocki? What?
Stocki is good. Yeah.
Stocki. All right. There you go. So Michael is the Vice President of Efficiency Programs at Efficiency Manitoba. And Efficiency Manitoba is, it's happened again. Nice presentation. Grab some ice cream. All right, there we go. Efficiency Manitoba is Manitoba's new crown corporation that's devoted to energy conservation. Efficiency Manitoba's legislated mandate is to reduce Manitoba's electrical consumption by 1.5% per year, and to reduce natural gas consumption by 0.75% per year. Michael is responsible for residential, income qualified, Indigenous, commercial, industrial, and agricultural efficiency programming. Michael has a bachelor's and a master's degree in mechanical engineering, and he's a registered professional engineer. Please share your thoughts with us, Michael.
Thank you, Kurt. All right, I'll fairly brief presentation. Really kind of trying to build onto some of the other things you've heard today. Basic overview, kind of focus on a little bit of who we are. We are a new organization, so I'll give a little bit of context there. And then I'll talk a little bit, provide some additional facts and figures related to the natural gas challenge in the province that we're talking about today. And then more specifically at the end, how we can take action today, what we can do, how Efficiency Manitoba can help. I will be mostly focusing on the commercial retrofit kind of market, but that was kind of just to draw a box around what I was speaking about today, but we also have other offers and programs for all those other customer segments as well. If there is one takeaway, the most important key message here is that energy efficiency considerations can be dealt with today, and they can, help reduce natural gas consumption, reduce GHGs, free up some of that electric capacity for those considering fuel switching, and Efficiency Manitoba can help.
Michael, so first, do you just want to turn your video back on?
Oh,
we'd love to see you.
Oh, that's interesting.
Just right in the Zoom.
Yeah, no, I guess when I shared my screen, it must have turned off on me here. Hold on a sec. Let's see if I can turn this on. All right, and you can still see my screen?
Nailed it.
Perfect, all right. I didn't actually turn off the video, I just shared my screen, but I guess it did it automatically. All right. So as Kurt mentioned, Efficiency Manitoba is Manitoba's newest crown corporation. Our effective date was April 1st, 2020. So basically we're just getting started here as a crown corporation offering energy efficiency programs and services devoted to energy conservation in the province. A couple things that make us unique: we do have legislated energy efficiency targets. So this is the first time that's been put into place in the province of Manitoba. So you can see our targets on the screen, and Kurt mentioned them as well. But overall, our objectives of our course to achieve those energy savings targets, to deliver cost-effective efficiency programs and services, and to create programs for as many Manitobans as possible to participate. And that can include rebate programming, incentive programming, services, educational programming, and other offers as well. We're currently operating in our first year of our three-year plan. So this plan was put forward before the Public Utilities Board last fall and into last winter, and it was basically approved prior to April 1st, 2020. Just a couple of very big highlights. related to this plan. If anyone's interested, you can go onto our website or the PUB website to see more details. But here I've shown kind of what our overall energy savings targets are on average over the next 3 years. To put those into context, you know, the gigawatt hours are the equivalent to heating electrically 21,000 homes. So that's a reduction per year. And on the natural gas side, it's the equivalent to heating 6,300 homes per year. So some very big numbers. And these are all higher than what's ever been achieved in the province before. So to illustrate, you know, on the natural gas side, our targets are 48% higher for natural gas savings, which again relates directly to GHG reductions as well. Another key component of Efficiency Manitoba is the involvement of private sector and an eye to our budget. So we do have a fixed budget over the next 3 years, and the key aspect of that is very little is actually kept internally for, you know, for administration, design, delivery of those programs. 87% of the budget basically goes back into Manitobans and the private sector. Essentially 70% of our entire budget is paid back to Manitobans in terms of incentive payments. A couple details on our GHG savings outcomes in particular. So, you know, the natural gas savings amount to 22,000 in our first year, 1,000 tons of GHG reductions, and those persist. For example, if you're improving the building envelope, adding insulation, improving, installing higher efficiency equipment, you are effectively reducing natural gas consumption and reducing GHG consumption this year, but those savings will persist for as long as that equipment is in place. So then essentially over the next 3 years, we have persisting cumulative GHG emission reductions of 140,000. And so that's an outcome just as a result that we're planning on achieving in just our first 3 years. And that's basically the equivalent to removing 5,000 cars off the road annually. So I want to next provide a little bit of context. I've heard a lot of facts and figures already related to the natural gas challenge and how affordably we can heat our buildings without natural gas. And I've got some additional ones. So I'll provide some of those. So with regards to electric and natural gas heat customers in the province, again, focus just on commercial right now. So electric heat, there's 11,000 customers within the province. And of course, natural gas distribution in the southern part of the province, there's 24,000 customers that heat with natural gas. Overall, our natural gas delivery, I got this graph here that's shown from Manitoba Hydro, straight from their annual report. Basically, I just graphed out their annual gas deliveries for that's entire province. So residential, commercial, and industrial. But you can see the fluctuations. And so this is not weather normalized data, it's just actual deliveries. So there could be like an 11% increase one year, 10% decrease the next year. That's subject to somewhat weather variation, but there's also an annual increase. And so if you look at all the differences on an annual basis, average them out, you get about a 1.2% per year increase in natural gas consumption. And so again, as part of the challenge, we've actually got natural gas deliveries in Manitoba increasing every year. So essentially going in the opposite direction of what we're discussing today. You know, another one of the challenges when you're looking at, when you're talking to a homeowner or a builder, commercial building owner about the end use economics of switching, you know, invariably this discussion on what's it going to cost me comes up. And so this, again, I've just grabbed this information to illustrate some of the challenges associated with that conversation. And this is coming straight from Manitoba Hydro's external website. And it's just looking at the annual space heating costs in a single family residence. So on the heat, there's a heat pump in the green. So that shows ground source, air source, a couple different air source options there, what the annual heating cost is. The natural gas, different efficiencies in the middle shows the breakdown of some of the basic charges, fuel charges, and the carbon charges. The light blue is the electric resistance heat at $1,450 per year. On the other side of the graph, it's basically the fuel, oil, and propane numbers. So again, definitely some challenges, especially if you're talking about asking someone to, as part of the discussion, going from a high efficiency natural gas furnace to something like electric resistance. Obviously, according to this, you'd be nearly more than doubling your annual expenses. And so that's obviously a challenge when you're talking to homeowners or building owners. This is part of the discussion, and this is usually what's front and center in many people's minds. So that's on the end use side, what the actual consumer will the questions they'll be asking. But of course, there's also the supply side economic question. And so, if there were some wholesale switching going on from natural gas, for example, to electric, there could be an increase in electric consumption in the province. And then the question becomes, what additional supply side resources are needed? Certainly from Hydro's perspective, they'd look to hydroelectric potentially. But I grabbed some data here from the US Energy Information Administration on where that price point, levelized cost of new generation services. So this is not at the distributed rooftop solar, for example. This doesn't look at that. These are like tens or hundreds of megawatts size projects. So they're definitely the larger, the supply side, generation side type projects. But this graph basically gives the levelized cost in US dollars, 2019 US dollars per megawatt hour. And so it shows a lot of variability of the range from the lower end to the upper end of those bars. Shows the range that are currently being expected for those generation resources entering into service in 2025. Of course, I include gas combined cycle in there as reference only. Obviously, if we were providing electricity by through gas, there's the GHG intensity associated with that. For the others, which are for the most part considered renewable, not the GHG impact, but certainly the cost resource. And so associated with any of them, there's going to be a supply side cost, and essentially electric prices will go up. From my perspective, why I've been in the field for energy efficiency for 22 years, and one things I'm really excited about is energy efficiency lies below all of those. Based on the values that we're putting forward in our plan, we're looking at basically equivalent on this value would be around the $20 per megawatt hour. So below all of those values is what we can achieve on energy efficiency when you look at our entire portfolio in the province. So, basically energy efficiency is the most cost-effective distributed energy resource. It can be ramped up incrementally, and as per the savings that we're achieving, it does add up to gigawatt hours. So some of the conclusions from the facts and figures that I've made, we're increasing our gas consumption in the province. Certainly when we start talking about fuel switching, it leads to challenging end use, it can lead to challenging end use economic questions and challenging supply side questions as well. And effectively, I think energy efficiency can really help address all three of those. By addressing energy efficiency, you can reduce both the gas consumption, but also on the electric side, so that when we do make more bold moves for fuel switching, you're freeing up that electric consumption so that you're not having to add as much supply as would otherwise be needed. So when you're, for example, if you're trying to sell energy efficiency benefits to your clients, customers, executives, or other stakeholders that you might be dealing with, here's just a list of some of the benefits of energy efficiency that you can speak to. And you have to understand from the audience's perspective what will resonate most with them and focus in on those benefits. But certainly there are environmental benefits, the social benefits, and the economic benefits listed of energy efficiency. And again, it's focusing and trying to tailor the message and use those benefits that will resonate most with your audience. But certainly, from the economics side, it's usually energy efficiency is a fairly easy decision. The paybacks are usually really attractive, or the return on investments are extremely high. Talking again about kind of the commercial retrofit and commercial new buildings, I want to kind of put up a slide here that shows, the breadth of the offers that efficiency and the programs that Efficiency Manitoba has in the market, or are coming to the market soon. So, as you can see here, there's a lot of variety in the offers. A couple highlights here: the ground source heat pump program. For the first time in the province, we're offering incentives for those customers looking to actually convert from natural gas to electric and switch to a ground source heat pump. So that's a new offer that's new in the province. Certainly, we've got electric savings programs here, as well as natural gas savings. Address the envelope, absolutely. And coming soon, some of the more aggressive, like deep energy retrofit programs where we're looking to, we'll be looking for projects that reduce end use consumption by more than 50% in a building. And they'll be designed as there'll be a building modeling component in their performance path option as well for that offer coming up. So again, lots of offers. The point is that, wherever you or your clients are in your journey towards energy efficiency, we've likely got a program for you. And there isn't really, when you're ready, or your clients are ready, Efficiency Manitoba is here to help. A couple examples on the, if you're making the economic case, really easy to do with energy efficiency. You're going to see, return on investments of 20 to possibly over 100%. Paybacks under a couple of years are not uncommon at all when you're talking about energy efficiency. You also can speak to the improved building functionality, more productive, healthier spaces. All of those benefits also can help set the stage for more aggressive or the longer term when you are looking to change fuel sources or make heating system choices going forward. It can also do a lot to help balance and optimize the heating and cooling loads within your buildings. So where to get started? Certainly I've included the link there, but basically get in touch. We've got newsletters, we've got the website, you can follow us on Facebook, Instagram, and Twitter, but that's really the first course of action. If you have an idea, if you're working with a client that would like to improve their energy efficiency, have a project in mind, get in touch with Efficiency Manitoba as early as possible to get the application in and to start saving energy and to receive an incentive. Thank you very much.
Terrific. Thank you very much, Michael. Great. Now we'll go to questions and discussion. The fun part, this is where and I noticed the chat has really been on fire here. There's lots of comments and questions and coming through here, and I've been hopefully Laura's been able to keep up with some of them. I've been trying to listen with the presentations at the same time as pay attention to what's in the chat. There was a couple of easy ones, or there's one easy one that comes to mind. Ken Klassen asked if the mandate that Michael shared with us for Efficiency Manitoba was a legislated minimum. And I'll just very quickly, Michael could talk to that, but yeah, that's what it is. It's Efficiency Manitoba has the mandate, those numbers, right, Michael? 1.5 and 0.35 or 0.75%.
Yeah, that's correct. And so I think I didn't quite see the question, but if that's the minimum, yeah, if we were to propose savings above that, certainly they'd have to be, we'd have to demonstrate the cost effectiveness of doing that.
Yeah, okay. So, but Laura, do you have a pick of the litter questions that really stands out for you that you'd like to ask?
I think it would be nice if anybody wants to just hop on and ask their own question. Sometimes it's just helps create a little bit of a nicer discussion and dynamic. So I see, Sandy, you had a number of questions. Did you have any that you wanted to voice?
Yes, there's seems to be more talk about converting electrical buildings to geothermal, but I'm wondering about ones that have the old boiler. A lot of homes in Wolseley, for instance, have the old boiler systems. And you know, you might also have a gas dryer because the electricity can't take an electric dryer, and you have a gas stove. So can you keep the old radiator system and work that with geothermal, or do you have to take out all the radiators, which would be a huge job?
A couple of comments about that. It depends on what temperature the hot water has to be to deliver the heat to that house. A lot of systems might be designed to operate at about 140 degrees Fahrenheit or so, or about 60 degrees C. But if there are changes made to the building, the glass is upgraded, if the insulation values are upgraded, ventilation system is upgraded, those kinds of things, the house is tightened up, you can often reduce the temperature of water that has to be delivered. In some cases, the gas boilers, just if they're not high efficiency boilers, have to operate at a minimum of about 140 degrees Fahrenheit, or about 60 degrees C. So some of the changes, using a combination of things, making the house tighter is going to reduce the heating loads, and it's going to reduce the temperature that you need to deliver that heat. So it can be done, it has been done, but there are other ways of doing that. There are systems where you can install fan coils relatively easily in that kind of a house that could replace the boilers. And you're right, it's not the easiest retrofit in the world. It has been done, and it can be done.
Thanks.
Ken, are you interested in asking
questions?
Oh, go for it.
Hi, I'm also in the Wolseley area and have looked at putting in geothermal to heat the house. And in our case, I was told at the time, this is a couple years ago, you needed at least 40 square feet of your backyard in order to excavate and put in the lines to pull out the heat. And a lot of the yards are actually too small for that. And so my thought was that if a couple houses went in on that together, they could share, they could excavate in the back lane between the houses and they could take the energy from there. Is that something that people are considering, or is there a change in the amount of space that you're needed to excavate in order to put in a system? And another thing I wanted to say, it was very interesting, Ed Lorenz talking about some of the different projects across North America. And just that we had some of the sewer lines in the front of our street were all redone this summer, and they were at a depth, I think, that would have been deep enough to put in geothermal. And I'm wondering if sewer systems that have to be put in with each house are being combined with access to geothermal heating.
Yeah, actually, one of the engineers that works with GeoOptimize, Connor Dacquay, has done his thesis on recovering heat from sewer systems, wastewater systems. That is being done in some places. It is being implemented in some projects. So yeah, that is fairly possible. And as installing sort of a small district system on a street, for example, if you can get the cooperation of the neighbors and everything else, it would be possible, for example, and you're right, in places like Wolseley, it might be difficult to get enough space to do that, but you could have a water well at one end of the block and another water to get well to get rid of the water at the other end of the block, and circulate water to each house, and each house could draw heat from that well water and dump it back into the ground at the far end of the street. I'm not aware of any projects around here that have done that. There's a project that was done a few years ago in Toronto where the city of Toronto allowed the use of the back lanes to install vertical boreholes. So those kinds of things are starting to happen. What National Grid and Eversource are doing in Massachusetts is basically exactly that, putting boreholes in the streets to connect up houses, commercial buildings, all kinds of things. Connor, did you have anything to add to that about this wastewater?
Yeah, I thought I'd add a couple things. It is getting more common, as Ed said. It's still not readily available. I think it was somebody on the line during the presentation said, you know, Manitoba is about 50 years behind the curve, and that's certainly true in most cases. You know, the wastewater heat extraction technology is taking off more in European countries. A lot of research in Europe has been done on that technology, and it is certainly becoming more and more available in Canada. But you know, the wastewater, it goes to the wastewater treatment plant at around 15 degrees C all year round. So there's an extreme amount of heat that's just being wasted and it transferred to the soil surrounding the pipe. So it's certainly a technology that can be used, and it's certainly a technology that should be used more.
Well, that's what I understand. That, like, Winnipeg has to do a lot of repair to the sewer system and upgrading of the sewer system, and it seems like that's one of the areas where you could obviously attach energy efficiency technology.
Yeah, that's correct. My specific research was on a technology that's called the source energy pipe. Essentially, it's a normal concrete pipe. The only difference is that there's a helical HDP pipe embedded within the concrete walls. So that HDP pipe circulates heat exchange fluid and extracts the heat from the wastewater to a heat pump through that heat exchange fluid. So in terms of cost difference from a typical concrete sewage pipe, it's quite negligible. You know, the cost difference between the two different pipes is it's a precast concrete pipe. So the material difference is the HDP pipe, and both are precast. So in terms of cost, it's minimal. It's just not a lot of people are investigating and looking into that technology because there hasn't been a lot of case studies done. So people are more or less scared of investing in this type of technology.
One comment I'd like to add for the question about installing systems in a place like Wolseley, for example. We did a feasibility study for the city of Woodstock, Ontario, about 2 or 3 years ago, looking at the potential of converting the entire city to basically a geothermal utility. Technically, it's very possible. The problem in Ontario at that time was that the cost of electricity is about 18 or 19 cents per kilowatt hour, but almost 3 times what we're paying. And the cost of gas is about the same, equivalent of about 3 cents a kilowatt hour. So the numbers didn't work. Technically, it can work. It is being done in some areas a little bit, not very common yet, but it is happening. There's a place called I think it's Whispering Valley in Austin, Texas, that they're doing a large, I think about 7,500 homes that are connected up to a geothermal system. We've looked at feasibility studies for a number of large-scale communities, 1,200 homes in California, that kind of thing. It is being done. It will be done. There's large players like large utilities that can amortize the cost of building the infrastructure over 60, 70, 80 years, same as what they're doing with gas lines. Problem with gas lines right now is most of the gas lines are amortized over 70, 80, 90 years. And if we're going to be carbon free by 2050, the numbers simply don't work. So in building more gas lines right now, you're building a stranded asset which is going to be useless in 20, 30 years.
I think I just want to continue the comments on this subject. I think we've touched on what is really essential here, which is that the distribution of geothermal or the utilization of geothermal needs to be undertaken as a utility, rather than as the caller from Wolseley talked about, you know, the difficulty of individual homeowners doing it themselves. And also, even if you make a partnership with your neighbors, they're now talking about a legality situation. And when you sell your home, what about the transfer to the next owner and all the rest of it? That's not where the responsibility should be with the utility, and the profits from it, which are, you know, ultimately realized, should be from, you know, take the worry away from the individual homeowners or building owners and put it on the utility. But currently we don't have a utility with that mandate, is my observation of this thing. And I just wanted to stress that. Other questions from anyone on the call?
I had another question for the Provens, which was they talked about using plant-based materials in their housing. And I was just wondering if he could talk a little bit more about that. And it's
Sure.
plant-based versus what?
Well, we use wood and cellulose in the buildings, wood for the structure, cellulose for the insulation. Cellulose is recycled, locally recycled paper fiber. And versus, for example, EPS or XPS foam or fiberglass, which is, some of it can be recycled, but typically the foam is a plastic product made from oil. It requires blowing agents or foaming agents, which are typically not, they're typically pretty terrible for the environment. The foam itself, at the end of its useful life, is very difficult to reuse and recycle because it's small bits of plastic that enter the environment. So we don't want to use those things which have tons of carbon thrown into their manufacturing and processing and transportation. We want to use products that are sequestering or taking carbon out of the air, which plants do, store it in their structure as wood typically, and then we can put that into the buildings, and the buildings can stand there for 200 or 300 years if built properly, storing carbon, buffering us from the terrible things that are happening now since we're not getting off carbon, and giving us a bit of time to try and solve the food and the transportation issues that were part of the presentation. So yeah, so plant-based wood, cellulose, there's, you know, cork, straw, they're growing mycelium foam from mushrooms to try and insulate. There's plenty of options. We've just chosen something that's readily available. It's local and recycled, and we've been using it for a fair number of years. The industry itself is used to using it, so it's not something that presents this huge challenge when you hear the word sustainable and green. They don't freak out. Yeah, that's all.
Thank you.
Okay.
Ken, I saw that you had a question in the chat. Did you want to vocalize that?
No, I think it was answered.
Okay, perfectly. Rob, I see you keeping on adding some more questions. Did you want to give some voice to some of those questions?
Yeah, sure. Two points very quickly. And first of all, big thanks to everybody who's presented on this and everyone who's participating. This is exactly the type of conversation that needs to be happening just so much more often. There's just great opportunities for our province here. My 2 points very briefly are, one, to my knowledge, there's at least 3 really big infill projects being considered in Winnipeg. There's probably more that I'm not aware of. But you have Capyong over in Tuxedo, you have the U of M Southwood Lands project, and then the Parker Lands one in Fort Rouge. I don't know if any of those are using green sources of heat or to what degree they're incorporating green design into their plans. It's going to be a huge missed opportunity if all of those thousands and thousands and thousands of new buildings are just hooked up to natural gas. The building owners are going to have to spend thousands and thousands of dollars a few years from now ripping out that system and putting in something that doesn't use carbon. So I don't know if anyone knows anything further about that, but that might be an idea for a future conversation like this one, a future lunch and learn if people are interested. And then my technical question, perhaps all 3 presenters want to speak to this. Given that there are economic savings available by taking a green approach to buildings, isn't it really just a financing problem rather than an economic problem? We already have lived experience here in Manitoba where it's possible for a building owner to not have to pay to have their home switched to geothermal, for example, if it was already using resistance heat. Aki Energy, an Indigenous social enterprise, has been operating for years, and they've shown over and over and over again that, you know, financing from hydro, in their case, paid for the entire installation up front, didn't cost the band, the community, or the residents any money, and the savings were then used to pay back that financing. So it didn't cost hydro anything to get that extra power. It's costing them a lot to build a new dam. This doesn't cost them anything. They provide money, they get all the money back out of the savings, and there's even enough savings left over so that the residents end up with a net positive financial result themselves. So particularly on those, you know, buildings that are using baseboard resistance electric heat right now, we should just be going like gangbusters, focusing on capturing that, providing more energy for hydro, and saving people money. I shake my head as to why we haven't done it yet, but maybe I'm missing something. So I'll stop there and turn it over to the panelists to chime in with their thoughts. Thanks a lot, Laura.
I'd like to add one comment, Rob. You mentioned the financing for geothermal systems, for example. Typically, the cost of additional cost or the incremental cost of installing a geothermal system is the cost of getting the pipe in the ground. There are ways in doing a design properly to really reduce that and actually provide a very positive return on investment. We did design 3 projects in Toronto. Remember, the cost of electricity is very high there, about 18, 19 cents a kilowatt hour. Cost of gas is about 1/6 of that. And by looking at really analyzing how the building is using energy right now, and these are like 3 existing buildings, anywhere between 75,000 and 175,000 square feet. Getting an inventory of how the energy is being used, gas, electricity, whatever, for computers, for lights, for heating, for cooling, whatever, and then building an energy model, simulating the energy use in the computer and calibrating that energy model to actual historical energy consumption gives you a very accurate analysis of how energy, what the heating and cooling loads are, how much heat we have to dump into the ground, pull from the ground. And I think I mentioned earlier that balancing the amount of energy going into the ground and coming out of the ground is pretty critical on these systems. You're managing your energy resource by doing that. By building in some of the energy efficiency measures that came out of the energy audit, the inventory, energy inventory of the building. What happens if we change the glass on the building? What happens if we add energy recovery ventilation system to that building? What happens if we change the insulation values on the walls? All of those things can be built into an accurate energy model, and you can see what the impact is of making changes to the building first. On all 3 of those buildings, we ended up with a simple payback of between 4 and 8 years. Return on investment between 15 and 25%. That's not a bad return on investment compared to getting 1% on your money in the bank. Yeah. That's a pretty positive rate of return.
Thank you,
So
Ed.
if I can,
Yeah, Don, please go ahead. I'll close off.
very quickly, as Ed's pointed out, the challenge isn't economic. The challenge is us realizing that this is doable. Like the German bureaucrat who got them off of nuclear power by demand side management, this is where Passive House came from. He said, the problem isn't technical, it's in our minds. And that's true. We can do this, we just have to choose to do it. And we have to get past the, you know, how much is it going to cost? We have to start looking at solid numbers about carbon. Ed had like the idea with geothermal, the district heating idea coupled with high performance buildings. Just why aren't we doing that? Like it's not, there's no technical challenges here. It's all policy and regulatory and choosing to go that direction. I think that's
having the city set policies that encourage that kind of thing is a big deal. City of San Francisco simply banned the use of natural gas in new buildings.
Yep.
Period. Can't do it anymore as of June 1st next year, I think it is.
And so finding alternative ways of reaching the targets, like, and so I'll quickly, Passive House just meld with geothermal and heat or heat pumps in general, because it's load reducing, and then you can use geothermal and heat pumps in general because you don't need the huge systems to heat your building. And
for example, in that Dakota project that I showed, if you that was able to heat 109 homes plus the other buildings at the current building level, how they're built today. If those buildings were built to better standards, you could triple that easily.
And to combine that with carbon, because if we don't talk about carbon, we're not addressing this issue of why we want to get off natural gas. All we have to do is choose how we do retrofit and build the new buildings, choose carefully, and combine it with heat pumps. And there's, as I said, the technical challenges, while present, can be addressed.
If we put the same effort into reducing carbon as we are to developing vaccines today.
Yeah.
Wow.
Yep.
Something I'd like to add is also your comments about embodied carbon. And this is coming from Wolseley in a brick house. The balance between the energy, the operational energy, and the embodied energy in a brick house or existing buildings is an interesting balance too. And I'm kind of looking forward to a discussion where we address the existing buildings and all the embodied carbon that are in those buildings, especially ones that have social or cultural value, even if they're not heritage designated, but have value that way, and how we can get them off carbon. It's not always easy in existing buildings to punch away at the efficiency, although there are measures, but to the extent that we might need to reduce the energy consumption, especially the heat loads on existing buildings, is an interesting balance when we're talking about getting them off carbon.
Well, that's one of the things that when we talk about, especially retrofits, existing buildings, everybody knows they're the elephant in the room. Again, I believe it's in our cultural and social approach to how we address this challenge. Because the challenge isn't the buildings. The challenge is how are we going to dump carbon? Because it's going to take a significant change in how we go about the job of civilization and society. We can't just talk about the building. As Kurt pointed out, there's food and other things that have to do to this. But some of the things are going to have to require us to think differently about heritage buildings, about how we are arranged in the landscape in terms of community and developing new community.
But I think also,
so when you talk about, oh, go ahead, Cindy.
Yeah, no, I'm just thinking also that we can't let perfect get in the way of progress. So even if we're able to improve that large stock of existing buildings, well, our whole stock, every building becomes an existing building, how we're able to prove what's already existing there.
Well, and that's, I think, if we look at we'll call it the CFAR tools, the further you go the first time, the more payback you get. So if it's doable once, then that gives us more space, and I call it buffer. That carbon buffer is what we're looking for, because we know that the other aspects of the economy aren't going to do this. So we need to use the buildings as the tool to give us time, because we don't have much time.
Agreed.
The year 2000, we moved back to the city and started building a high-performance building. That was 20 years ago, but it was like that.
Well, and I would like to say there's been a number of projects that have happened in Wolseley where actually when they put in the green space at Gordon Bell School, they pulled out an old district heating system that was connected to a bunch of apartment blocks in the Wolseley area. So that had been disconnected years before. But that was another thing where there was a deep dig. They could have put in a geothermal system or something like that. And there's been other places where buildings are coming down and there's access to the ground. And if the city and the province were together on this and pulling projects together, I think we could get more things happening in these older areas.
So we just had a question from Norm here.
Okay, yeah, thank you. So the current Manitoba Building Code has trade-off amendments in National Building Code Section 9.36 regarding insulation thickness, HRV, and drain water heat recovery. So currently, new houses are required to have HRV and drain water heat recovery if there's a basement installed, but are permitted to have thinner insulation. So I just want to ask the panel's view, do you like Manitoba to keep these amendments when we adopt the NBC 2015? Right now, Manitoba is mandated to harmonize with the national code, which says insulation should be thicker, but HRV and DWHR are not required, and only to keep amendments that have compelling reasons. Your thoughts, please. Thanks.
Yeah, I won't be able to address that directly, probably without looking into it a little bit more. But I mean, you know, looking at our climate and where you're going to get the energy savings, it's going to come more through the envelope than through, you know, just the HRV and drain water heat recovery. So certainly, you know, would definitely be a proponent of increasing the insulation rather than lowering it. You know, our work related to efficiency codes and standards is, you know, looking past the 2015 one to future codes like the 2020 and tiered codes, for example, to set the stage for, you know, what are those different pathways to get to even deeper reductions, like upwards of 70% in building stock, for example. So if you don't mind sending me an email, I wouldn't mind looking into your question a little bit more, though.
Thank you.
Yeah, the code changes are sadly lacking. You pointed out that Manitoba requires a heat recovery ventilator. There's a minimum efficiency that's mandated. And if you look at 90% of the new buildings built, new houses, and you take a look at their HRV, that HRV will only meet that minimum. And so that means they're putting in the bare minimum again to meet the code requirement. So if we want to make any changes to increase the performance, you have to raise that lowest possible bar so that the buildings get better. And there's a couple of jurisdictions, Michael can probably, and Ed, and I mentioned it, the city of Vancouver has a pretty aggressive step code to try and get to net zero fairly quickly. So that would be my, let's go and take a already established set of parameters that are very aggressive and lead to an actual target, and use that instead of reinventing the wheel or going backward in this case.
Yeah, and our efficiency programs, like specifically for new homes, you know, they look at the base code and they say, okay, now what can we do well above and beyond that to increase that efficiency, and let's basically address those incremental costs and try to, you know, through incentives, basically cover that cost. So there's no or very little incremental cost to go well beyond code in those higher efficient buildings. So that's the design of our programming, essentially, so that there isn't a compromise there. You're not just building to code, you're going well beyond that and getting an incentive to do so.
Thank you.
Okay. Oh, sorry. One last question. I know that there's more questions to be asked, but I see a hand up and I can't wrap it up while there's still a hand up. So Melvin, good move there.
Hi, sorry about that. For a commercial strip mall, if you were to convert it to geothermal and you have rooftop units, what happens to the rooftop units? Are they still reusable? I'm sorry if that sounds like a stupid question, but.
No, it's that has been done in some projects. There are heat pumps that are designed to simply replace the rooftop units. They tend to be more expensive than heat pumps that are designed to be inside the building. The Seasons of Tuxedo Mall, they were built with heat pumps that were suspended from the ceiling close to where the rooftop units would normally have been. So it's quite possible to do that kind of a retrofit. We'd have to see the strip mall itself to see what would be the most cost effective. My own thinking in our climate is that it would be better to have the heat pumps located inside where they're not exposed to the climate that we've got, but both are possible. Another way is to have heat pumps that produce hot and chilled water that can be fed to air coils that are in the existing rooftop units that can be retrofitted. That's also been done. It depends on what shape the existing rooftop units are in. If that's it'd be site and project specific, but yeah, that's been done and can easily be done.
Okay, I guess I'm more thinking of a roof that's just been upgraded from R4 to R40. But you know, in the future, thinking of geothermal for that particular property, even replacing all those rooftops with something that is geared for geothermal, but if it's something that is doable, and I'm hearing that it is.
It is absolutely doable. And one of the benefits of getting equipment off the roof, it avoids potential water leaks, that kind of thing. If you have the equipment inside, it's going to be easier on the equipment than having it exposed to SOAR minus 30, minus 40.
Yes, well, the roof doesn't have any leaks currently.
Yeah.
Due to a big roof job.
Yep.
Thank you.
Right.
That would have been a great opportunity to replace the rooftop units, shut the holes in the roof, and put the heat pumps inside.
Too late now.